Section 10.4, Finding Equations of Exponential Functions. So in the last section, on those last couple pages, we started playing around with some tables and graphs and functions and starting to see how those were related to the equation of an exponential function, and we're going to start practicing that a little bit more formally in this section and building up some more tools to help that become an easier job for us. So let's look at another example with the table. Some values of functions are provided in the table. Find a possible equation of each function. Use either a linear or an exponential function. So the first thing you need to do for each one of these is sort out, is it linear? Because if it's linear, we'll use the form y equals mx plus b. Or is it exponential? Because if it's exponential, then we're going to use the form y equals a times b raised to the x power. So we need to sort out which of those two types is it, and then we can try and fill in either the m and the b or the a and the b. So the way you sort out which type is it is you look at how you're getting from one value to the next. If it's multiplication, it would be exponential, where we have a multiplier of b. If it's an addition or subtraction, then that would be linear, where we have a constant rate of change. So when I look at this one, this is either plus 9 or times 4 to get from 3 to 12, right? 3 times 4 is 12, and 3 plus 9 is 12. But if I try 12 plus 9, I don't get 48. I get 21. But if I do times 4 again, I get 48. Times 4 is 1792. Times 4 again is 768. So it looks like this is a times 4 multiplier. And when you have that, that means it's going to be an exponential. So f of x is an exponential function, and its a always comes from the y-intercept. So our y-intercept is the y value that goes with an input of 0. So the input is 0, the output is 3. That would be a. And the b is the multiplier, which here is times 4 all the way down. So that would be times 4 raised to the x power. Let's look at this one. Here, if this is a multiplier, it's messy, because 19 times something to get to 13 would be a messy value. So I'm kind of hoping this is a minus 6. So let's try that. 19 minus 6 is 13, minus 6 is 7, minus 6 is 1, minus 6 is negative 5. So it looks like as we move from one to the next here, it's by subtracting 6 each time. And when you have a constant rate of change like that, that's linear, and that rate of change is the slope. If your x is going up by 1, the change in y represents the slope for a linear function. So this would be your slope, so that's m, and the y-intercept would be 0, b, and so this would be the b in a y equals mx plus b situation. So g of x is linear, and the slope is negative 6, so negative 6 times x, plus the y-intercept is the y that goes when the input is 0, the y value is the output, and that's the b for the linear, so that'd be 19. So here a constant multiplier, exponential, the multiplier is the base, the y-intercept is the constant out front. Here we have a constant subtraction, so that makes it linear. That constant subtraction amount is the slope, and the value that goes with 0 is the y-intercept, which for a linear equation is the b. So there's a couple of them. Let's move on to h. This looks like possibly a plus 7. Let's see if that's really the trend. 2 plus 7 is 9, plus 7 is 16, plus 7 is 23, plus 7 is 30. So it does look like this one has a constant addition of 7. That means that's linear, and that also would be the slope. And then this would be the value of b for the y-intercept. So it looks like we have for h of x a linear function because it's a constant addition, where the added value is 7, is the slope, and the starting point of 2 gives us the b for our y-intercept. So h of x equals 7x plus 2. On this one, it looks like possibly that would be a division. I always think it's easier to see multiplication, so let's go up instead of down. It looks like 2 times 4 would be 8, times 4 would be 32, times 4 would be 132. So it looks like if I go up, it's times 4. But when we do this, we want to think as the x gets bigger, so we want to work in this direction. So if going up is times 4, then going down would be divided by 4, or times 1 over 4. So let's just check that and see if it works, since that's a little bit of a messier one than the others that we've been working on. So I'll start off with that 512, and my theory is we're moving down the chart by doing times a fourth. So let me do that, times 1/4. is 128, times 1/4 is 32, times 1/4 is 8, and times 1/4 is 2. So it looks like I have the multiplier right, so that multiplier would be the base of the exponential b, and then the y-intercept, and this is the y-intercept piece because it has a 0 input, that would be the constant out front, which would be a. So k of x, because it's a constant multiplier, not an addition subtraction, looks exponential, and the constant out front would be 512 times the base, which would be that 1/4 raised to the x power. So a couple different things to learn there. One of them is if you have a constant multiplier like we did for f and for k, then it's exponential. And if it's a constant subtraction or addition, then it's linear. And for the exponentials, which is the new one, when you figure out that multiplier, you're figuring out the base b. And when you figure out the y-intercept, you're figuring out that constant in the front, which would be the a. Alright, we also saw in the previous page that sometimes when you're filling in a table you have some gaps, and sometimes the gaps are more than just one square, and that led to us solving some equations like this. So I just want to formalize that practice on that algebra. So they want us to solve each of these and round to the nearest hundredth. So if we have 5b squared equals 45, we want to get the b squared by itself. So I want to get rid of that 5, which is a multiplier, so I would divide both sides by 5. That gives b squared is equal to 9. And on the previous section, we just thought about that and said, alright, what would you square to get 9? And we said the answer would be 3. Here what we want to do is do some algebra to try and get the b by itself. And so we think, what's the opposite of squaring something? And there's two answers. One would be to take a square root, and the other one, which we just saw a couple sections back with the rational exponents, would be that you could take that b squared equals 9, and you could raise both sides to the 1/2. And remember that if you have a power to a power, you multiply powers. So 2 times 1/2 gives you b to the first, or just b. And then what is b? It's 9 to the 1/2. But on equations like this, when you have an even power, well, actually let's just go ahead and do this on the calculator. The square root of 9 should be 3, but let me show you that with the rational exponent as well. If I take that 9 and raise it to the 1/2, then that gives me the 3 that I expect, which is the square root of 9. But we're actually missing something, because even though 3 squared is equal to 9, negative 3 squared would be equal to 9 as well. So anytime you take an even root, or you start out with an even power and you take a fractional exponent, there's actually two solutions. There's the 9 to the 1/2, but also the negative value as well. So when we have an even exponent and we do this fractional exponent on both sides to get the letter by itself, we have to catch both answers, we have to do plus or minus. So the answer actually would be plus or minus 3, and that's a little bit messy there, so I'm just going to rewrite it one more time. Our answer would be that b is equal to plus or minus 3. And if you test the negative 3 back in the original, you'll see it works just as well as the positive 3 does. Alright, let's go ahead and try this again with this 5th power. Just like we tried to get the b squared by itself there, we'd try and get the b to the 5th by itself here. So I would add 8.2 to both sides. Those cancel off. And then that's a little bit messy, so I'll just go ahead and use the calculator to do the addition there. So 237.5 plus 8.2 is 245.7. And now we're trying to get this b to the 5th by itself, so I want to get rid of that 2.1. The 2.1 is connected by multiplication, so I'll divide both sides by 2.1. So those cancel. And then we get b to the 5th is equal to, let's see, let me do that on the calculator and see how that comes out and see if it's messy or nice. 245.7 divided by 2.1. That's a nice number, so I'll go ahead and write it down. If it was messy, I probably would have just left it as a fraction rather than round, and we'll see that in some later examples. So now I have b to the 5th equals 117, and I want to get that b by itself. So when I had b squared, I could take a square root, or I could raise both sides to the 1/2. When I have a b to the 5th, I could take a 5th root, or raise each side to the 1/5. So that's what I'm going to do here, is raise each side to the 1/5. Now this time I don't know the answer. I knew that the square root of 9 was 3 in my head, and I verified it on the calculator. This time I don't know what the fifth root of 117 is in my head, but I can still approximate it on the calculator, and it says to round to the nearest hundredth, so we'll go to the calculator and do that on this one. And let's see, if we take 117 and raise that to the 1/5, then we get approximately to the nearest hundredth, that's 2 decimal places, we get about 2.59. And when you have an odd power and you take the fifth root like this, you do not get a plus or minus, you only get the positive root. And I want to go ahead and show you that real quick. Let me back up and show you the answer to A2. If I want to check the 3, I can take 5 times 3 squared, and that should be equal to 45, and it is. On this one I would take 2.1 times my answer, 2.59, raise that to the 5th power, and subtract 8.2. And so what I'm doing there is just plugging that into the left side of this equation. So if that is really a solution, I'll get 237.5. And I actually get 236.55, which is close but not quite right. The reason it's not working perfectly is just due to rounding error. So let me go ahead and show you something here. If I take the 117 and raise it to the 1/5, I'll get the answer with all its decimals. And there's a way to plug that in directly with all the decimals, which is to hit 2.1 times, and now it's time to take that number and raise it to the 5th power right there. So above the negative it says answer, or ANS, which stands for answer, and if I hit the second key and then ANS, it plugs answer into that spot, and that is all of these long decimal version of that fifth root of 117. So when I do that, I'm plugging in all those decimals into this B, and then subtract 8.2. And I believe that is the solution before the rounding error. So when I do it now, I should get 237.5. And I didn't because I forgot to raise it to the 5th power. So let me go back, get that answer again, and let me type that right. 2.1 times my answer raised to the 5th power minus 8.2. There we go. There's the 237.5 that I was supposed to get all along. But what I wanted to show you is that if you tried that with a negative, 2.5 times negative 2.59 raised to the 5th power minus 8.2, we don't get anything even close to 237. So the positive and negative works when it's an even power, but with an odd power that's not true. And again, the reason this didn't work perfectly when I plugged this number in is because I rounded it, and rounding brings in error. So you get something close to the solution, not the exact solution. Alright, so here's a quick summary of all that. If you have b to some power equals k, then what you want to do in either case is raise both sides to the 1 over n. And if it's an odd power, your only solution is what you get when you take this side and raise it to the 1 over n. But if you have an even power, then you get two solutions, both plus or minus. And you might remember that the square root of a negative is not a real number. So if you have b to an even power and this is negative, then there's actually no solution at all to that. Alright, we'll go ahead and look at some more examples as we continue on. Alright, let's go ahead and look at solving using roots like 1/2 and to the 1/5 power and see how that fits in with finding the equations of exponential functions. So find an approximate equation of y equals a times b to the x of the exponential curve that contains the given ordered pairs and round to 2 decimal places. So we have 0, 8, and the 0 is really special. That's our y-intercept. And on an exponential function, which has the form y equals a times b to the x, the y value of the y-intercept is always that constant out front, a. So as soon as we see that, we actually got to start on our equation. It's y equals 8 times b to the x. Now this one is not the y-intercept, but it's on the graph, and that means that it's an ordered pair xy. So x is 4 and y is 79. So I can plug those in. The y value is 79 and the x value is 4. And then I want to figure out what that b is. So what I would do is try and solve this equation, and this is a lot like the two equations we finished up with on the previous page. So I'm going to get the b to the 4th by itself by dividing both sides by 8. That doesn't go in evenly, so I'm just going to leave that as a fraction. Let me write what I have here, switching the sides. I have b to the fourth equals, I'm going to put this in parentheses, 79 over 8. And I'm trying to get that 4 to go away. So the opposite of raising something to the fourth power is to raise it to the 1/4. Remember, you multiply exponents, so 4 times a fourth is 1, and those would just cancel. And then for balance, I'm going to raise the other side to the 1/4 also. And if I do that, I'll have an approximate value for b. And I'm going to go to the calculator for that, and it says to round to 2 decimal places, so that's what I'm going to do. So these guys cancel, and b is approximately what I get if I go to the calculator and put in 79 over 8 raised to the 1/4. And actually that's exactly what b is equal to. When I go to the calculator, I'll get an approximation. I wrote this in kind of a strange way, but that's the way it looks on the calculator. So let's go ahead and bring that in and have a look. So I need to put those parentheses that you see there to make sure that this is my whole base and that that is the whole power. So parentheses 79 over 8 raised to parentheses 1 over 4 and end the parentheses there. And then rounding to 2 decimal places, I get about 1.77. So that's my base, b, and we already know the a value of 8, and so now we can take this base right here and we can plug that in for b, and we'll have our exponential function. So y is approximately 8 times 1.77 raised to the x power. When you have your final answer, it's going to have a y and an x in it. So just like our goal in finding the equation of a line was to figure out m and b, our goal in finding the equation of an exponential function is to figure out the a and the b. And once you have those, you write it with those plugged in, but the y and the x still there as variables, still allow us to make predictions as we move forward. Alright, let me show you another example. This one's very similar, it just happens to have some messier numbers involved. But again, there's a 0 right here for the x, and that means that the y-coordinate is a, because when there's a 0 here, this is your y-intercept, and the y-coordinate of the y-intercept is always the a in the y equals a times b to the x form. So we get the value of a basically immediately. This one right here gives us a value of x and y, and we're going to plug those in, and we'll plug in the a at the same time. So for y, I have 17.1. That's equal to the a, which is 97.2, times the b, which is a mystery, raised to the x, which is 4. And then I'm going to try and get that b by itself. So the first step would be to get b to the fourth by itself. So I would divide both sides of this by 97.2. When I do that, that'll get rid of this coefficient, and the b to the fourth will be alone. But we got to do that on both sides. And that definitely looks like it's going to be messy, and I don't want to round yet, so I'm just going to leave that alone. And let me write it out. I have b to the fourth equals 17.1 over 97.2, and I want to get rid of that fourth power. So the opposite of raising something to the fourth would be to raise it to the 1/4. And the same thing on this one, raise it to the 1/4. And these will cancel. And so b is going to be equal to whatever I get from the calculator when I put in 17.1 divided by 97.2, all raised to the 1/4. And we'll go to the calculator and round that to 2 decimal places as requested. So let me clear that out, enter in the new one. So this is going to be 17.1 over 97.2. I almost forgot to put the open parentheses, so I went back and inserted that in. And then that's going to be raised to the 1/4. And round that to 2 decimal places, so I get that b is approximately 0.65. So I knew a right away. Now I know the value of b. And so I can go in and plug those in and say that the function will be y equals a, which is 97.2, times b, which is 0.65, raised to the x power. And that would be my function. One other thing to note on this page before we move on is that we said on the previous page that when you have an even power you get two solutions, a plus and a minus, and that is true for this equation. Both 0.65 works and so does negative 0.65, but for exponential functions our base is never negative. So even though this equation has two solutions plus or minus, only the positive one makes sense for our base. And the same thing was true on this one. Both plus or minus 1.77 would solve this equation right here, but for an exponential function we're looking for the base, and only the base can only be positive, so the negative one doesn't make sense. Alright, one more thing before we move on. I want to show you that even though we did these by hand, it's also possible to do them on the calculator. If I took this ordered pair right here, 0, 8, and thought of that as an x and y, 0, 8, and then this one, 4 and 79, and put them in this chart, then if I take those values and put the x's in L1 and the y values in L2, I can use a regression process like linear regression, only this time an exponential regression, to find that same equation. So let me go ahead and bring in the calculator and show you that. So to enter that data, we would want to hit Stat and go to Edit. I have some old data in here, so I'll clear that out. Enter in the x values 0 and 4, and the y values 8 and 79. And then I would hit Stat and go to Calc, and before we were choosing linear regression, but if we arrow down all the way to 0 we get an exponential regression. And if I press enter on that one and then tell it where my data is, L1, L2, it'll give me a regression equation for an exponential function, and it'll tell me the values of a and b. And notice it says a is 8, which is what we got, and that b is approximately 1.77, which is also what we got. So I showed you how to do it by hand, but the calculator can do it well, and that's going to do it as well, and that's going to be important to know when we move to the next page. Alright, so moving on to page 16, we're continuing to try and find equations of exponential functions, rounding the a and b to two decimal places. And so we're trying to get an equation of the form y equals a times b to the x. And on both of the previous problems we had a head start because we knew a right away. But a isn't 1 and a isn't 7 because that's not 0 and that's not 0. In order to read off the y value and say it's a, the x value has to be 0. When you don't have that ordered pair, you can still use algebra, but the algebra gets a lot messier. So just before we finish the last page, I showed you that the calculator can do linear or an exponential regression to find these equations, and it turns out that exponential on the calculator doesn't require us to know the y-intercept. So what I would do is follow that pattern from the previous page, turn this data into an xy table. So the first ordered pair is 2, 1, the second one is 5, 7, and then I'm going to want to take this data and put it into L1 and L2 on the calculator, and then I'm going to want to press the Stat button, choose the Calc menu, and then instead of choosing linear regression, I'm going to go further down to exponential regression, which looks like EXPREG, and put the L1 and the L2, and the calculator will directly give me the values of a and b, and I can just use them to write down my equation. So let me show you that process on the calculator. So I'm going to press Stat and Edit, and I still have that data from the last problem, so I'll clear that out. And then I'm going to enter in these new values. The x's are 2 and 5, and the y values are 1 and 7. And then I'm going to press Stat, like I'm saying here, and Calc. Go over to Calc, and then down quite a bit until you get to exponential regression. Press Enter, and then tell it where your data is, L1 and L2. So second L1, comma second L2. And the calculator will do all the work for us. So y is approximately an a value of 0.27 times b, which is approximately 1.91 raised to the x power. And so that's going to be my exponential function. And notice the a isn't either of our x coordinates because, or our y coordinates, because we didn't have a 0 for the x coordinate. And I just want to show you that this equation works. It's not going to work perfectly the way I've written it because of the rounding, but if I take 0.27 times 1.91 and raise that to the 2, I should get a number close to 1 because I'm plugging 2 in for x. The y value should be the one that matches on the table. And I don't get 1, but I get close to that, and the difference is because these values are rounded. And if I do the same thing, 0.27 times 1.91 and raise it to the 5th power, that should give me a value close to 7, and I get 6.86. And again, that's not real accurate, but we only put 2 decimals on this multiplier, so I can only trust a couple decimal places on this, so it's about 6.9, pretty close to 7. Alright, let me go ahead and show you that one more time. This time the values are messy, but to be honest with you, I really don't care that these are messy. These were nice, but I used the calculator. When they're messy, I'll still use the calculator. Alright, so my xy, the first one is 4 with 6.3. Notice since that's not a 0, this is not the y-intercept, and this is not a. The next one, 10, 250.8. Again, that's not 0, so that's not the y-intercept, so this is not a. But I'm going to let the calculator take over from here, put this data into L1 and L2, and then just do the same sequence, stat, calc, exponential, regression. So let's take a look at it. This is still the last one, so I'll clear that out, press stat and edit, get rid of that old data, put in the new x's, 4 and 10, put in the new y values, 6.3 and 250.8, and then stat, calc, arrow down to exponential regression, tell the calculator my data is in L1, L2, press enter, it'll do the rest, and y is approximately a, 0.54, times b, 1.85 if I round it to 2 decimal places, which is what they requested, raised to the x power. And if I plug a 10 in there for x, I should get out this y value of 250.8, so let's try that. 0.54 times 1.85 raised to the 10th should be close to 250.8. I get 253, which isn't that close, but that's because we rounded these so much. If I take the 0.54035922136, in other words the whole value of a, times 1.847840566, the whole value of b, and raise that to the 10th, I should get 250.8. And I get 250.799999. So there's still a tiny bit of error in that because even those numbers that I plugged in were rounded, but you can see that if I put more decimals I get really close to that y value. Alright, one final example with this procedure, and that is what if instead of giving us 2 ordered pairs they give us a graph. Well, the key thing to remember is that the graph is actually a picture of infinitely many ordered pairs. So what I want to try and do is find 2 of them that are nice meaning integer values. This one seems to be an intersection right on grid lines, so what is that? That is over 2 and up 3. And I want to find another point that's also right on grid lines, and that looks like this one would do. That one is over 3 and up 2. Sometimes people ask why not use the y-intercept there, but if you look at the y-intercept, it's not 7, it's a little bit below 7, and so now I'm guessing, is it 6.8, is it 6.7? I'll go ahead and put a guess down. The x is 0, and the y is maybe 6.8-ish, but again, I don't know exactly what that is, so I don't want to use a point that's a guess to do my regression. I'd rather use the ones that are nice ordered pairs like this. So I'm going to use those 2, an x of 2 goes with a y of 3, and an x of 3 goes with a y of 2. And then I'm going to put those values into L1 and L2 and let the calculator do the rest. So let me bring that in, clear out the old stuff, go to stat and edit, clear out those last ordered pairs, and then enter in the new x's, 2 and 3, and the new y's, 3 and 2. And by the way, it's really important you keep those orders. You can't just rearrange it. It's got to be an ordered pair left to right. And then stat, calc, exponential regression, data is in L1, L2, and it'll tell me the equation, which I'll write to 2 decimal places. So y is approximately 6.75 times a base of 0.67 raised to the x. And just a quick comment, this number right here tells me the y-intercept. So apparently the y-intercept was, we write it in a different color, but the y-intercept was apparently a 0 and 6.75. So you can see that my guess was close of 6.8, but not quite right. And I just want to show you one other quick thing that you should do when you're using the calculator to do regression, just to check your work a little bit. You should think about whether things are growing or decaying. So here, as x gets bigger, going from 2 to 5, the y values get bigger from 1 to 7. So this is a growth function, so our base is bigger than 1. Moving on to the second one, as the x goes from 4 to 10, the y value goes from 6.3 up to 250. So again, as the x gets bigger, the y gets bigger. That's growth. And notice our base is bigger than 1. This one we can see, just looking at the picture, is a decay. It's decreasing as we move to the right. You can also see it in the ordered pairs. As the x goes from 2 to 3, the y is going down from 3 to 2. And notice that when you have a decay, the base is supposed to be smaller than 1, and we got 0.67. So it's good to kind of confirm that base matching the growth or decay, since we're trusting the calculator to give us all the numbers. Alright, that's it for this section.